distribution for the low energy theory of the original lattice model near the critical point. And the mass of this free formula is just given by the 2J times the difference to the critical point, which is just corresponding to the 1 over the correlation length of the system. And exactly at this critical point, you will have that the correlation length approaching to infinite, which suggests that in the system you will have some scaling invariant, also the dilation invariant of the original field theory. And in the 1+1 dimension, if you have a quantum field theory with the Lorentz transformation, the translational invariant, and together with this dilation invariant, you will have some conformal symmetries for the quantum field theory, which suggests that at the critical point, this massless free formula field theory is a conformal field theory, and it is known as a one minimal model of the conformal field theory, where the central charge is given by 1/2. So the excitation of this model is given by the spin flip, which you create a pair of domain walls, and the domain wall will propagate freely in the space. However, now let's think about some deformations to the original critical point that we add a longitudinal field perturbation at the critical point. So now we have a small HD term here, so the perturbation. So the original domain wall propagation process here will be confined by this HD term. This means that once you flip the spin, every spin flip will cost a certain amount of energy, and it will not make this domain wall propagation too far away from the original point. So this is a similar mechanism as the three-dimensional QCD part confinement. So somehow you can treat the pair of domain walls as a pair of part, and they form as some mesons, which in the elementary excitations, collective excitations of this low energy model. We can still write down the low energy field theory of this original lattice Hamiltonian, and the sigma operator in the language of conformal field theory, and put it here. This field theory is a perturbed conformal field theory. So actually, due to this perturbation is a relevant perturbation, since the scaling dimension of this sigma is given by 1/8. So it will strongly modify the IR physics of the original field theory. However, it is proved that this field theory enjoys infinite many local conserved charges commuting with the Hamiltonian. And here we label such conserved charges by using the language of the conformal field theory. So the S here is a Lorentz spin, which is a difference of the conformal weight for the corresponding operators. It is proved that, it is partly proved and partly conjectured that the complete set of this S is a prime of 30.
So when you consider the longitudinal field, you mean that it's still
particularly describe all the excitation. So the quasi-particles are labeled by the capital A here, where the small a is a type of the quasi-particle system. So somehow this is not a +1 it's more or less like any in the 1+1 dimension. But nevertheless, so in the following, I will introduce you how to obtain this conserved charge and how to obtain the particle spectrum of this corresponding model. So then I will introduce firstly, I will introduce the Zamolodchikov dimension counting method to partly prove that this perturbed conformal field theory is integrable. And then I will show you how to do the S-matrix bootstrap to obtain the mass spectrum and the S-matrix contents of the corresponding integrable quantum field theory. And finally, I will show you how to use the form factor bootstrap method to calculate the matrix elements of this perturbed conformal field theory. So first of all, let's consider this Zamolodchikov dimension counting method. So actually, this one method has a lot of different names, but in the original paper, Zamolodchikov did not give this method a name. So you can see in many different papers, they call this as Zamolodchikov method. But nevertheless, so I will give a brief introduction to this one. So let's consider some conservation laws in terms of the 1+1 dimensional conformal field theory operator contents. So here I describe all the operator contents in my field theory using the language of the conformal field theory. This is not just suitable for the pure conformal field theory, but also suitable for the deformed conformal field theory. Since it is just the equivalent to that, I choose different bases to describe my field theory. So if you consider the conservation laws for certain types of operator with with the Lorentz spin S, you will find that the conserved charge, the global conserved charge Ts composed of the local conserved charge density Ts plus 1 and center S minus 1, where these two operators will satisfy this result. That is, the partial bar Ts plus 1 will equals to the partial theta S minus 1. One of such example is given by the stress energy. You change this to the holomorphic and anti-holomorphic coordinates, then you will obtain this relation, that is partial part T equals to 1 minus 1 over 4 partial theta. So I redefine this theta equals to minus 1 equals to 2, since the stress energy tensor in the conformal field theory is the descendant field of the identity operator. So it will have the spin S equals to 2. And the trace, the theta is actually the trace of the stress energy tensor, which has the S equals to 0. This is very easy to argue, since the trace of the stress energy tensor should be invariant under the Lorentz transformation. So it have the S equals to 0. For pure conformal field theory, this is just gives you partial bar T equals to 0. Since conformal field theory is traceless, you do not have the result for the trace of the stress energy tensor. But for perturbed conformal field theory, let's take an example here. So the perturbed conformal field theory is given by original conformal field theory perturbed with some primary field. Then if you still consider the family means that I start from the identity operator, and I can use the vectorial algebra to generate all the descendant field of this identity operator, such that I will obtain a conformal family. So stress energy tensor is one of this conformal family. So I can prove all the J alpha satisfy the conservation laws. This is very simple. Just directly put in the result and find it satisfies the result. So following this way, I can construct infinite many conserved charges in the pure conformal field theory. This is also a proof that the conformal field theory being integers, being all the integers. And however, in this operator set, not all the operators are linearly independent with each other. So this is not a irreducible representation. Just like I can give you an example. So I can consider another operator, which is given by the Ts minus 1 alpha, and I use the first vector algebra L minus 1 to apply on this Ts minus 1. This is equivalent to the partial Z Ts1. And if you calculate this partial Z Ts1 in the J operator, you will find that it will connect with the J alpha operator with this coefficient. So they are not linearly independent with each other, such that if I want to consider a reducible representation, I will have to consider some modular. So in some, I will consider the operator sets in some quotient space, which is given by the lambda s hat, which we quotient this L minus 1 apply on lambda s minus 1. So this is how we obtain the conserved charge, the pure conformal field theory. However, now I'm having a perturbed conformal field theory. So you remember that the original questions we care about is the conformal field theory with a relevant primary field perturbation. So for perturbed conformal field theory, you remember that now the trace of the stress energy tensor is no longer 0. But now I have this relationship between the theta and the phi operators. So it is equivalent to say that I want to find some operators in the original. So this partial ZT corresponds to this lambda height. So in the original lambda height set, I want to find some operators which can be equivalent with this partial Z theta. So this is what I want to do here. So let's first see what's the partial Z bar T here could affect to the corresponding operator set in the perturbed conformal field theory. So I can consider a mapping of the DN operator. I can construct a DN operator. So this DN operator actually is given by that I map the lambda size of mapping. And if you calculate this, due to the fusion rule here, you can prove that the DNA just belongs to this phi set. And then you further calculate D0, you find that the partial bar just equivalent with D0. So we find that the partial is the opposites. So now, if I want to make this relationship satisfied, I have to have some additional mapping. The additional mapping is between the lambda set to the L minus 1 phase. So, but I have proved that the partial bar here is back the lambda set to this phi set. So you should have two mapping here. The first mapping is given by lambda to the phi s hat. The second mapping is lambda to the L-1 files. So you have both the mapping set. Since if they are equivalent with each other, then you will only have the mapping between the left S hat, that's plus Y hat, to this phi S plus the below formalism. And for the minimal model, further for the minimal model. So let's consider some minimal model with the measure here. The minimal model is that we have the central charge of the minimal model given by this formalism. We have P equals to 3, 4, 5. And the primary field is given by the below result for the conformal weight. So if P equals to 3, this corresponds to our case. That is, we have the minimal model of central charge 1/2 with the perturbation given by the sigma operator, which the conformal weight is 1/16, such that the scaling dimension is 1/16 plus 1/16 equals to 1/8. So putting this result into the above formalism, we can write down the two results for the characters, the kind or the characters of the corresponding operator. So you can obtain this two formalism, and you just expand this two formalism and compare the coefficients of the Q. Since the coefficient of the Q is just the dimension of the corresponding operators. So if you extract out the coefficient of the Q, you get this result. So you find that for the dimension lambda S plus 1 larger than the dimension, so sorry, there should be a cascade. Nevertheless, for the dimension lambda S plus 1 larger than the dimension of phi S, we have some non-trivial space given by this set. So it's a 1, 7, 11. 13, 17, and 19. So you'll find that this gives you part of the conservative charge I mentioned in the very beginning for the quantum ES in the field theory. But this is not the full conservative charge. The reason is that the dimension counting method cannot be applied to the operators with too large Lorentz spin. The reason is that so you see the argument I mentioned above, I mentioned just now, is that you see this is just a necessary condition. So we only consider the periodic by effects, and also we only consider the necessary ones that y the dimension is larger than this one. We will possibly have the mapping between the two operator sets. So this is just a necessary condition, and you cannot guarantee that for the large spin case, this will still hold for the calculation. As far as I know, there's no further development or prove the conservative charge for this perturbed conformal field theory, but I don't know if just like the Ising conjecture. This conjecture is that he thinks the complete set of such spins is given by the prime of T. So he directly said that now we prove the several of the previous spins, and we just guess that the complete set is given by prime of T, such that this model will be integrable. So
I didn't follow very closely, but I Ising conformal field theory actually has no energy condition in relation to power.
Yes, right. This is actually the spirit of the truncated conformal space approach. So you can write down the new Hamiltonian in the basis of the original conformal field theory, and you do the diagonalization, you can obtain some new results for the state. But that's not some modification that you can describe in 1 or 2 sentences. It's very complex, and you can only see that effects in numericals. So yeah.
So then
Yes.
Change the spin.
No, in the original conformal field theory, since the conservative charges. So let me go back to this page. So you can see, as you can see, the dual conformal field theory will have the conservative charges, which is generated by the identity operator, which means that for all the integer spins, there are so many conservative charges anymore. But you can prove following this method, you can partly prove that not so it breaks the whole conservative charge set, but it left some conservative charges, and we find that the set I should not say we find that, but our logical conjecture that such conservative charges are still infinite many, but this infinity is not the original infinity. It's given by the prime of T, not the whole integer values. So this is the point. Yeah. Okay. So let me keep going on. So let me remind you this page. So now we have partly proven, partly conjecture this complete set of the conservative charges. So what's this? What's the information that this conservative charge could provide us. This is given by so actually you can treat the conformal field theory as the UV limit of the conformal field theory. The reason is that now we consider the perturbation. This perturbation is a relevant perturbation. So it will open the gap in the IR limit. But in the field resistance, once this H is smaller than infinity, you always have the RG flows from the UV to the IR, and the UV is still governed by the original conformal field theory. So the conformal field theory, the perturbed conformal field theory will provide you some information from the UV limit. And for the IR limit, it is governed by the integrability. So we know this is an integrable quantum field theory, and we will use the information of the integrability to show the mass spectrum and also the other information, just like the S matrix. So I will give you the introduction to the S matrix bootstrap. So first of all, for the integrable quantum field theory, the S matrix of such quantum field theory is given by the so-called factorizable pure elastic S matrix. The factorizable actually means that for a multi-particle scattering process, you can always decompose them into the combination of a two-particle scattering process, just like given by this equation. And the pure elastic means that during this scattering process, there will be no particle creation and no particle annihilation process. Namely, you have how many particles get in, you have how many particles get out. So this is the meaning of factorizable and pure elastic. So then this will suggest to you a very important information. That is the scattering, the order of the scattering does not influence the scattering amplitude. Namely, you have the 1, 2, 3 particles, the 1, 2 particle scattering, then the 2, 3 particle scattering, then the 1, 3 particle scattering. It's equivalent as first we have the 1, 3 particle scattering, 1, 2 particle scattering, and 2, 3 particle scattering. So if you change the order of the scattering, it will not influence the scattering amplitude. And for n equal to 3, this generates the hallmark of integrability, which is known as a Yang-Box equation. So in this case, we can actually constrain the property of our scattering matrix. So the very important two properties is known as the unitarity and the cross relation. So if you can generate some functions, these functions satisfy the unitarity and the cross relations, then these functions could be treated as a matrix, which corresponding to the so-called factorizable pure elastic. This is the idea. So the unitarity and the cross relation, more importantly, will provide one, where the simple pulse, there will be some pulse structure in the S matrix, where the simple pulse corresponding to the bound state. So you can understand the bound state from an imaginary process. Or I can say this is an intermediate process. That means I have a big particle scattering, and then in the middle, I will generate an imaginary particle given by the C particle. And after this process, is the whole particle spectrum. So based on this relation, we can actually do some calculations, and you will find some relationship between the AB and C particles. The first one is given by the energy momentum conservation. So you consider momentum during the scattering process being conserved. So the total momentum of the AB particle will be equivalent as the momentum of the C of the S matrix given by the bound state. So all the rapidity here are given by the pure imaginary number. So the original cost function will become some cosine function. So this provides you this mass triangle relation for the 3 types of particles. And again, the Yang-Box equation provides us the correspondence between the scattering amplitude between the 2 scattering processes. So if I consider one additional particle, namely the D particle, then the scattering amplitude between DB and AD scattering angle. So just count a very simple geometric relation on this figure. You will obtain this matrix bootstrap equation. So this is the second equation that this process will satisfy during this integrable field theory. And the final one is given by the conserved charge bootstrap equation. How to understand this? This is also very simple. Since we have mentioned about this conserved charge at the corresponding N state. So if I consider this is a multi-particle space between A and B, then I should have a conserved charge here. And I modify this A and B particle as a C particle. I should also put a conserved charge here. These two conserved charges should be equivalent with each other. So this is how we obtain we can solve the mass spectrum of the corresponding integral field theory together with the original conserved charge obtained from the perturbed conformal field theory. So let's do this for the quantum EM integral model. Let's first assume that there will be only one particle in the spectrum. So this is just an assumption. I only have one particle in my integrable field theory. So first of all, this ABC equals to 1. So I can cancel this QSA, QSB, and QSA, and I can obtain this equation. The scattering angle is due 1, something like this. And I can solve this scattering angle, which is given by 2 over 3. And to sides is given by prime of 6. So if I only have a So if I only have one particle in my quantum EM integral field theory, then I will have the Lorentz spin of the conserved charge is given by prime of 6. But you remember that at the very beginning, from the perturbed conformal field theory, I have shown that the conserved charge of the quantum EM integral field theory is given by prime of additional information during the scattering process. So the most simple additional information is that let's assume there's a second kind of process you can consider here, just like A1 to A2, A2 to A1, and A1 to A1, A1 to A1, and A1 to A2. But here for the simplicity and to give you the result that is, if you consider these two scattering processes, you can obtain two equations from the conserved charge bootstrap equation. And these two equations could help you to solve the scattering ratio to the M1. So this is a very famous hallmark of the quantum EM integral model. And also from this conserved charge bootstrap equation, I can obtain the conserved charge for this scattering process is given by prime of 10. So somehow prime of 10 and prime of 6 gives you prime of 13. So you should choose the common set of this two scattering. I will provide you why this is not the end. So now everything is beautiful, right? I have the prime of 13 as the conserved charge. I have two particles, and I know the scattering angle of these two particles between 1 and 2. So I can try to construct my S matrix. So the construction of the S matrix is based on some building block. So I first have some building block which specify the unitarity and the cross relation. And then I have a production of all this building block based on my particle information. Then I can obtain my S matrix. This is the logic. So here I have two particles. The two particles have their own scattering angle. And this scattering angle corresponds to the simple pole of the corresponding S matrix. So I can solve this scattering angle given by x equals 10, given by this combinations of this S function. However, this result is not true. Why? Since now we have used the two equations. The one equation is the conserved charge bootstrap. The other equation is this mass triangle relation to solve the information of the particle contents. But we still have one equation, which is S matrix bootstrap. So if you take this S matrix into the S matrix bootstrap, you will find that the solution is not correct. This solution does not satisfy constraint given by together with the constraint given by the conserved charge. So you remember the conserved charge is given by prime of CT. Together with this one, we obtain the mass spectrum and the S matrix contents for the quantum EM integral model. So then you can do some numericals to check if the result is correct. One of this method is known as the truncated conformal space approach. So people use this method to really check the mass spectrum, and they found that the mass spectrum indeed satisfy all these relations. So it's actually partly proved that the topological conjecture is correct, since he did a conjecture that you will have such a masses, and we already found this masses.
Everyone see the constant at the exponent.
Yes.
Exponents like the use. So this exponent has also related to single class.
Yes, right.
And what about the rest of
the M2
And
and
all scale like this one.
yeah, they all scale like this. The reason is that all the masses are just in unit of M1 times some constant. Yeah, so they all scale in this relation. Yeah.
So that's why its mass are actually determined by the universality class, the components, the original.
Yes. Yes, 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 right.
The constancy you have you obtain from the content.
Yes.
The ratio M2 to M8 to the M1 is constant.
Constant.
In the Ising universality, the M2 to M8 ratio, the ratio of M2 to M8 to the M1.
They are obtained from the S-matrix bootstrap. So
Maybe the Ising universality is a constant.
yes. So they satisfy. Actually, if you have the Ising universality class and you put the longitudinal field perturbation, you can always obtain such ratios in the field series sense. So in the lattice model, you might not see the heavy particles since the field series only describes the lattice model in the low energy sector. So yeah, can partly say something like that, but maybe it's not so suitable to say the excitation is not so exact. Yeah. But one of these physical picture is given by the confinement. So you have this confinement, and these two domain walls, so the two parts, and they combine as a Ising. So I have different numbers of such confinement as they combine with each other together.
This is the bound states. That's what not different vibrational different bound states of these signals.
You may say something like that, I think. Yeah.
So I don't want to talk about numerical this
Yeah, finally we will show some. I will show some numerical result. Yeah, but yeah, okay. Yeah. 对，它这是完备的，这是一个 minimal 的完备解。
然后你加到几我把地方，它永远是 minimal， 若干 minimal 是从还是其他的。
就是你没有任何办法可以加到这个，就如果你解到第8个的话，你想加到第9个，那么你没有一个方程可以这样的。对。Yeah, finally, I will introduce a little bit on this form factor bootstrap to solve the matrix element for the corresponding integral field theory. So we care about the matrix element. Why? Since we want to calculate the two-point correlation function, right? This corresponds to some experiments in the reality, and the advantage of the integral field theory, different from the Euro quantum field theory, is that once you want to calculate the two-point correlation function, you don't need to really calculate perturbativity by using the Feynman diagram and do it order by order, but you just need to expand the two-point correlation functions with the corresponding factors will satisfy some basic equations. So these are 5 basic properties equations of the corresponding form factor, which was firstly provided by Mianov in 1992 in one of his book mentioned about all these 5 properties. Form factors for the Lorentz scalar is only related with the difference of the rapidity of the corresponding particles. And there will be 2 additional properties, namely the exchange property and the cyclic property, which will provide you a minimal solution of the form factor. And the kinematical singularities, bound state singularities, will provide you a solution for the multi-particle form factor. I will show you this later on. And for the Ising conformal field theory, actually we can solve the form factor for the primary field of the sigma operator and epsilon operator, corresponding to sigma z and sigma x. And this can also be corresponding to form factor for the identity, but that's a little bit trivial. For the other types of form factors, you really need to generate it from some additional constraints. So let's just focus on these 2 types of form factor. So we will have a general on-that solution of the form factor. This is based on the structure of the S matrix. So in the S matrix, we have the minimal solution of the S matrix, and we consider the whole S matrix as a production of the minimal solution for the S matrix. Then it is also natural for us to consider some general on-that solution given by some polynomials in terms of exponential of theta, which provides you with the information of the operator itself. So this part is the only part for the operator, and this provides you some information for the S matrix. So if I consider this minimal form factor, I can put this minimal form factor in terms of these two equations, the extension property and the cyclic property. I will obtain two equations here, obtain these two equations here. So let me remind you a little bit about the minimal S matrix. I put it here. You can solve the minimal solution of the G function. This is known as the DOZZ formula, which is the same in the linear quantum field theory. So we have this G function. This is a minimal solution. So actually, there are some formalism to solve this G function. So this is a very old result, and you will have some asymptotic behavior for this G function, which is given by exponential zeta over 2. And you can also construct the D functions. So this D function is provided by the behavior of the G functions. The logic is that so let's see these functions. So this is some polynomial of the Q functions. So together, these three parts, you should not have some divergence behavior for theta goes to infinity. So this gives you appears in terms of the pole structure for the S matrix. You still have one additional constraint, which is given by the UV. If you make the UV limit of the form factor, this will give you some upper bound of the divergence behavior, whereas H is a conformal weight of the corresponding operator. So based on this result, you can determine all the upper bound for all the order for the polynomials of Q, F, and D functions. So let me give you some examples here. So you can write down the two-dimensional form factor in terms of this part, and the P functions is given by for the two here. So this P functions is given by some polynomial of the Cauchy function, and for F1, F2, you can exactly write down the P functions here, where you have 5 coefficients in front of it, and you can also use the maximum expected value. So this is some causal laws, causality laws of the independent with each other. So this provides you some asymptotic behavior of the two particle form factors, and then based on this two normalization results, and also together with the original pole structure of the form factors, the same equations, you will obtain 3 groups of solution. The 3 groups of solution corresponding to the 3 primary field: identity operator, the sigma operator, and the epsilon operator. Somehow you have to identify the different operators through some different method known as the topological C theorem and its modification. But here I do not introduce that part since that will be too lengthy. And once you know this matrix element, based on the solution and the energy cut. So here you can solve based on the information of the form factors. You can solve the two-point correlation functions and its spectrum in the energy momentum space. So this is the so-called lemma representation. You just need to calculate the norm of the form factors and then plug in this result to it and integrate out it. The scale that the neutron scattering experiment could observe. And we know the information of the X and Z, so we can directly calculate the X and Z. However, for the sigma y, for the original Ising model, we still have the correlation function for the sigma y part. So the sigma y part could be obtained from the sigma z part. You can do a commutation relation for the sigma z operator to the Hamiltonian X. And based on this relation, we can calculate all the correlation functions for sigma x, sigma y, and sigma z. Let me show you some results here. Okay.
The relationship between the DYY and DZZ is expressed for all the Ising uniform. Or
well, it's not so correct. You have to ensure that the commutation relations are not modified by the. It's like if you have a pure transverse field relation of sigma z and the Hamiltonian. The Hamiltonian is given by the summation of sigma z plus sigma x. And this will provide you the result for this one. And the Hamiltonian acting on this state will directly give you some energy. So this is why. So for this one, it still holds, just like you have
relation of the vector, ultra Cartesian O,
of the element. The 2-point correlation functions between certain operator and the stress energy tensor and the trace of the stress energy tensor. That will provide you the scanning dimension of the corresponding operator. And you sum over of the corresponding operator. And you sum over all the 4 factors. The result will approaching to the corresponding scanning dimension. That is another way to check it if the result is correct. For the quantum yield integral model, this is asymptotically correct. You can never obtain the correct result like 1/8 or 1/1 or just 1. But you are seeing that as 1 or just 1. But you are seeing that as many 4 factors as you calculate, it will approach to that result. But for some other type of integrable quantum field theory, just like the Ising integrable quantum field theory, namely you define that case, this result is exactly correct. So yeah, this is another way to check it. I did not introduce it here, but yeah. Finally, I will show you some spin dynamics. So you can calculate this by the channel of different particles. So you set the single particle complete basis, you open some direct functions corresponding to the single particle. And you can also insert the 2-particle complete basis. And you find that there will be some Markov singularities in the threshold of 2 different types of quantum particles. The reason is that this is actually comes from the divergence of the density of states. This will provide you the Markov singularity. However, for the two sum of particles threshold, it will not have this divergence. Due to that, the 4 factor will coincidentally have 1 additional term, and this 1 additional term will exactly cancel this divergence. So there's no Markov singularity in the 2 sum particle threshold.
Okay, is the result of the Ising. It is the result of transforming Ising model.
No, this is the result for the yield case. So you have a transverse field Ising chain plus a longitudinal field. Yeah.
And then actually the exact result just presented numerically.
Yeah, exactly.
Any calculation just from your equations.
Yes, from the field theory result. And this is a multi-particle continuum. It's relatively trivial, but if you want to calculate it, it will cost a much more computation source. Since the multi-particle form factor is very hard to calculate.
So
yeah.
I'm just curious. So as you get this kind of spin dynamics, can you actually study like transport property spaces?
Yeah, that will be a little bit harder since the transport. So first of all, you have to define a conserved charge, a conserved current for the transverse field Ising chain, right? So for the transverse field Ising chain with the longitudinal field, it is a little bit hard. So maybe you can calculate the Hamiltonian, I'm not so sure. And then these types of calculations were based on the thermodynamic properties of the integrable model. That will be also very hard. So if you want to calculate some quantities for the integral model in finite temperature, this will rely on some additional techniques, and that techniques will cause very a larger difficulty to calculate. But that had some results 10 years ago. PLL in 2014, he calculated some small quantities in that paper, I think. Yeah, but on the quantum yield. Yeah, quantum yield. Yeah. And
that means quantum E8 are they are only 8 methods, but only a few particles.
Yeah, only a few particles.
Only a few particles.
Yeah.
So its impact on thermodynamics is observable. Suppose they do not contribute.
You mean finite temperature?
Oh.
Yeah. So first of all, if you want to calculate some finite temperature result, you have to make the temperature approaching to 0 for the integrable model.
Very low temperature.
Yes. In the very low.
The low temperature thermodynamic by this low energy excitation.
Yes. Not so reliable. Yeah. And this can be applied to some materials. This material is known as the BCVM. So you have this is through structure this material quantum critical point corresponding to the Ising solid data. This critical point will be shadowed by the 3-dimensional antiferromagnetic order. And in this model, the 3-dimensional antiferromagnetic order exactly provides the effective longitudinal field for the 1-dimensional chain. So that's why it provides some environment to realize the quantity and particles. So we can do some experiments, and this is a neutral scattering result. So due to the form periodicity, you will have some random folding effect, where you have you can see that this is in the middle from the boundary to the center, and near the center, this is a region that the quantum field theory will be applied. So this theoretical result is given by the quantum field theory, and it's normalized by the corresponding effective speed of light and also the corresponding energy scale. So you can compare this result exactly.
How should I read it? So the horizontal axis is H1Q versus M1. M1 is mass.
Yeah, MYC. So this is so you can treat that the MYC is the universal scale of the corresponding scale. This is momentum scale.
Momentum.
Yeah. And you still have a moment energy scale.
Yes, I should use this momentum. Actually, momentum scale.
And also
M1C is momentum. M1 is the mass.
here the My is modified. The My is modified by the C square. So actually, this My is not directly corresponding to the yes. So you can compare this result. And actually, this provides you some effective speed of light in these materials. It is given by the almost 1,600 meters per second in this material. So this is upper bound of how the information spread in this material. And this is the zone center result. So we use two different types of inelastic neutron scattering in two different temperature pocket and measure the result and identify all the corresponding peaks. So and finally, I make a acknowledgement. So this is a theoretical guide. These are the theoretical guide. First of all, I have set my supervisor for me to sit down to the guidance of all these series of works and 理论上康定这个方法本身不可以对大尺变异大不用。就一旦这个 S 变得很大的话，这个方法就不适用了。就是说，里面有个 power bar 这个东西呢，它是把兰布达办不到这个 phi 上，对不对？准确的说，它是把兰布达 height 兰布达 S plus one height 办不到 phi S height 上，对不对？但是如果我想让我的这个 conservation law 成立，我需要把兰布达 S plus one height 办不到这个 phi height 的这个极的5级去，这就意味着我的兰布达 S plus one height 这个极的大小必须要比我的 phi。
然后还有一个问题就是我不是很准确，但是你看最后的那个部分是那个谁还是就是1+1
动力学谱，所以说动力学谱其实是测的这个东西，就这个两点关系函数，就是我可以去算一个时空的两点关系函数，然后对这个时空两点关系函数做一个复叠变，只在就这个材料它刚好它的这个一维切片点在这个三维里面很近，然后你可以通过转恒场的方式调这个切片点的位置，然后你发现，对转场的这个，对，它可以调切片点位置，你会发现一旦下面点转，对是的，如果你转一下，它人臂就会变大，对，最大可以到40摄氏。我这个自旋二分之一其实跟我的这个场是有一个 distortion， 大概有5度左右。而如果你转一个场的话，induce 的这些 additional 就是转力的时候，这个质量，转到110的时候，就交叉的时候，是转，对，差不多40特斯拉，是这个相比到40，对，
它的那个，
对，
如果那样的话，加40克，就是加40克那个实验室也没有一个真的，
那个好，那个好，可能是我这不知道，不是，
那个他没看到地位的，
对，这个
40克它就跑了，
对，是，
就是说你相当于在那个系统上，你把那些
对，是的。那这个只在 K 等于0附近是，因为 K 等于0附近，它的这个丁格可以被调到描述，所以
对吧？不是一个那个粘合的，不能写的，是一个有东西的，然后这个东西就是可以通过三维的那个效应，到它那个动。可以变成这个
这个三维反面是的这个，对，差不多类似于那样。我不是这个方面专家，我就不开，我不开。对，
学那个模型盘，还有什么？你这个可以算在线吗？没有问题，
这些没有问题。
我们手机就是你这个算数学难，8个比，因为它那个 还是围绕后的一个东西。
不是，这原因是因为1/8的这个 form vector 它 somehow 它不是一个非常标准的函数，就是它这个 Q function 你求出来以后，它是一大堆这个数值的系数加上这个 exponential 得到的，所以它事实上是有数值精度的。但是你其他的一些可计场呢，比如说一星啊、三高呢，它那个 Q function 就是一个函数，所以
那
比较
这个会结合一下那个数值函数，
有可能可以，这个 possible 也是可以。
就能搞的话，你方块它，但是你方块它的话，你得算就算运动动力，你算静态的比额里是不看。
那样的话其实不需要用到这个1/8场论的信息，因为这个场论其实给不出，你会发现我在求这个 form factor 的时候，我其实是把这个真空期望给弄过来，真空期望其实被我弄过来的啊，就这个场论其实没有办法告诉你真空期望的这个大小，所以它其实
上面写绝对值，
对，放了绝对值，这个算一个
没上相对的，
对，是这样。
但是你相对理论那个，
I don't know，一般做过，这取决于具体它的公式写成什么样，对不对？这个得看。
如果你不算一些这个比例，
I see，OK，可以算，但它算出来效果怎么样，还有这个难度大小是另一码事。